please try to put on this side.
Right.
Oops. What? Help.
Hey, boy, you are helpful. Thank you much.
This one is a difficult
Okay.
one. Let's see. Here, I think it's good.
Okay, thank you much. Put this back. Oops. I can put it on like this too. Okay. Yes, that
way.
way.
There is.
Okay. Okay. So what do I need? Not much.
Hey,
Hi.
how are they? Oi. Oi.
Não, mas tá, mas você estava na física, não era? Ou você começou? Eu fiz iniciação com o Paulo. É por isso que eu lembro de você lá. Você estava aqui no IAG mesmo.
Depois da gravidez, meu metabolismo se mudou completamente.
É, o meu depois dos 40.
O meu teve uma combinação.
Você tem quantos anos?
40.
4.0? Eu fiz 41, falei, agora eu sou um Opala 6 canecas. Próximo carro que é marca é o Dodge, 5.6. Ô, professor.
Fica online depois, né? Gravada a apresentação.
No YouTube fica.
Fica, né? Não, Facebook não, mas no YouTube.
Facebook não. O que acontece nas do YouTube é que não tem ninguém editando. Então, por exemplo, você tá filmando, agora filma tudo isso aqui. Você começa às 12h15,
sim.
a pessoa tem que avançar 15 minutos até.
Beleza, eu vou falar pra ele mudar isso.
It will be recorded
Okay.
on YouTube.
Yeah, you can see it later on YouTube.
Oh,
You can see your own self.
Oh, actually, they're already recording. It starts recording 10 minutes before. So I think it's already on.
Smile. Smile.
Yeah, and if you want someone to see you right now, you can send the link. We can see you live.
Mas ele te deu os slides? Esqueci. Ah, não te deu? Sempre digo. Esqueci. Tava vindo todo dia, semana passada. Eu falei, será que agora a aula é?
Oi?
Os slides.
And do you have the presentations of your class somewhere in the? I think you sent me a Google Drive, right?
yeah, yeah,
Did you put everything there?
yeah.
Ah, okay. And, some people
It's
are
all
asking,
there.
so I can.
It's all there.
It's all about you now.
Yeah. My fault.
Oh, Professor, because I asked him the slides, he didn't send.
Yeah.
Because I could not come this week.
Yeah, it's okay.
A lot of meetings, bureaucratic meetings.
Oh
this
yeah,
week.
that's perfectly fine.
Let's wait 5 minutes.
Yeah.
Brazilian time. Spain. Precisa sim.
precisa readaptar-se, porque esse negócio vai ficar grave. Então. Depois de 36,1 de segunda-feira.
Por isso que a minha casa nova tem ar-condicionado na casa inteira.
Ah, você deve ter passado bem, Rondônia.
Não, eu tinha 20 anos.
Não, é a nova Raquel.
Raquel depois que levou.
Eu sempre tive uma facilidade muito grande de acreditar em qualquer tipo de clima, mas depois dos 40, o problema da regulação térmica se eu sinto muito calor. Agora frio, uma fotozinha lá de a menos 17 de camiseta.
Eu descobri que abaixo de menos 10 é tudo igual.
Você vê? De dia. Eu achei que isso era verdade o tempo todo. Eu fui andar à noite.
Eu não tenho acesso a isso.
Você pode baixar, puxar para o seu disco, o seu disco se compartilha. Até uma cópia. Yes, gera o seu drive. Tem transferência de dados, mas só cópia. Já tem como subir suas transferências.
So is it called IAG Institute or IAG Department?
The department is atmospheric science.
Ele me enviou, que ele pegou visualizar a parte dele.
Se monitora o Facebook aí. Monitora o Facebook pra ver. Eu fico no YouTube. Eu vou ver no celular também. Tem que estar logado? Tem que... Eu não sei. Então, o computador está sempre logado. É que eu não tenho acesso do YouTube. Eu tenho do Facebook.
Whenever. When do you think, Rachel? Should I start now?
Just a second, I need to monitor for questions on YouTube and Facebook.
Oh, okay, go ahead, yeah.
Yes. See? It's live. Don't worry, there's not much people.
I see one or two.
Tão frio que ela fica tão interna na conferência, ela 7 graus. As pessoas dão palestra, você já fumaça.
Edmilson, está no YouTube? Você está no YouTube?
O filmar foi do ano naquele dia, na época. Depto. Não adiantou nada.
E aí, pessoal, boa tarde para todo mundo. Então, hoje a gente vai ter a apresentação do Andrew Heimsfield, pesquisador lá do NCAR. O NCAR fica lá no Colorado, na cidade de Boulder, nos Estados Unidos. Ele trabalha lá desde a década de 70. Ele foca o estudo dele no granizo. E o estudo dele de hoje vai ser o último artigo dele que ele fez sobre o crescimento do granizo e diversas características em função do tamanho do granizo. Então ele vai dar um resumo para a gente do que ele anda fazendo nos últimos anos. So, I'll get started.
Thank you. I want to thank the University of Sao Paulo IAG Institute, Atmospheric Sciences Department, for inviting me. And Mikhail has been wonderful as a host, and Mikhail Cicchini, and Rachel Albrecht has been fun to be with, and a number of professors that I've enjoyed very much talking with. So I have worked on hail for a long time, but I started off my early career working on hail, and then more recently have taken it up again. The problem does not go away, and it's just interesting. Okay, so I will talk about Graupel and hail, and I'll explain what all these things are. So the outline of my talk is as follows: where the hail does, well, I won't go into what that means, but occur and how the hail does happen. And then I'll give you an overview of hail occurrence, how hail is observed, and some of the basic characteristics of Graupel and hail, and then measurements that have been made. And I do want to talk about how hail forms, and then something about hail suppression. Okay, according to the American Meteorological Society Glossary of Meteorology, Graupel is basically small hail. So Graupel is heavily rimed. Rime are little water droplets which collect on a snow crystal or an ice crystal, often indistinguishable from very small soft hail, except for the size convention. So Graupel is small hail, less than 5 millimeters. And in my opinion, there is an extremely blurry boundary between Graupel and small hail. Graupel and hail shapes, they can be conical, cone-shaped, hexagonal, or lump. And this shows the global distribution of hail. And here we are. Well, it's not surprising where we find it, for the most part, and some out here. And these are the Andes, of course, and that's a hot spot. In fact, the most intense hailstorms in the world are over this area of Argentina. And then if we go to Africa, so the South African portion is a hot spot, as well as here. And then in Asia, some. India has lots of hail. Europe doesn't have a lot of hail. And, but India does. Okay. So hail storms have been observed from satellite. So this is AMSER-E, estimated severe hail, all months. And it's color-coded according to how often it occurs. And so here we see, you know, these are the hot spots right here. North America has lots. This dividing line is kind of interesting because basically that is the Rocky Mountains, and so it's east of the Rocky Mountains. And look at Africa, plenty, but South Africa seems to be a hot spot, India as well. And there's some in Europe and some in Australia. Okay, next view graph. So I picked a couple of locations just to show you where hail occurs and how often it is. And so this is the observed annual left and trend of the mean potential hail index over a long period of time. So this is Spain, Portugal, this area here. And the Alps is a local hotspot. And the trend is upward. And any guess why the trend would be upward? studies, I'll show you in a few minutes as well, have shown that there are more people to report hail. So that's a main reason. And this just shows hail reports per year as a function of year. And this is over the United States, this is over Australia, and this is over Europe. And you see the progression. And it has to do with population density, for the most part. Well, I'll say a little bit more about that later. Now, Brazil. Okay, so this is a paper by Martins in Atmospheric Research 2017. And this shows hail reports and as a function of number per square kilometer, and the topography is shown here. So it looks like, again, maybe mountainous terrain is a trigger point. And this shows time series of annual number of hail reports for Paraná, Santa Catarina, Rio Grande do Sul, and other states for the period of 1991 to 2012. This is that same article. And so, you know, it looks like there's an increasing trend. And that trend they have associated with population density. This is the United States hail reports, total hail reports for that period, long term. And what you see is, again, the Rocky Mountains stretch along here. And what happens with elevated heat sources is that the higher areas, the mountains, heat up much more than the air at the same altitude, but over, let's say, well over the land area. So that hot spot heating is a trigger point, as well as the topography creating lift. And clearly you can see that here. And this is the total hail reports greater than 2 inches. And so these are hot spots. And I'll get into just a little bit of that later too. And I went yesterday into some records just to show you kind of some examples. These are early reported hailstorms in North America. So earliest one reported was about 1928, and 7-inch, 17.8 millimeter hailstone weighing 680 grams is believed to be the record largest known in the US at the time. And then there was one in Southern California, which is extremely rare to get hail. Los Angeles, another one, blanketing the region much like a snowstorm, and that's happened here too. And then the first largest one really recorded was 14 millimeters in diameter and 760 grams. That fell in Coffeyville, Kansas. And then this one, a violent 40-minute hailstorm bombed Fort Collins just north of Boulder with hail up to grapefruit size. 2,000 homes and 2,500 automobiles were severely damaged, and about 25 people were injured. And in fact, one hailstorm I know of killed a child. It went right through the windshield of a car. And this is Europe. So 1360, a freak hailstorm struck and killed an estimated 1,000 English soldiers during the 100-Year War. And then here's another one, thought to have incurred fatalities, most intense in record, 1697. And you know, you just see, this is Germany, severe storms. So Britain gets some too. And these are the largest hailstone sizes by country. So this one, Saskatchewan, a stone in a diameter, heaviest. So that was 290 grams. And another one here, 7.8 centimeters. And then Bangladesh, 1 kilogram. That's a lot. And then this one I will give you a little more detail on. This one was 20 centimeters, huge, and very, very large. And then another one, Germany, 14 centimeters. So those are some of the largest reported in each of those countries. So, as I said, we talked about hail, precipitation in the form of balls greater than 5 millimeters. Large hail can have lobes. They grow by the collection of liquid water that freezes on the surface of the hailstone. And spheroidal hailstones often exhibit a layered internal structure with layers of ice containing many air bubbles, alternately with layers of relatively clear ice. And if you slice a tree, you see tree rings. And those tree rings are a result of the fact that there are seasons where the tree grows more, some grow less. You know, certain seasons they grow more, certain grow less. And as a result, you get rings of growth. And that is the same thing with a hailstone. The layering is indicative of perhaps different growth regimes. And large hail may contain liquid water within them and be spongy, kind of like a sponge. And the density of small hail is typically relatively low, sometimes much less. And small hail may be indistinguishable from larger graupel. And I don't like the convention, but it is what it is. Okay. Okay, so how is hail observed? So one way, which you probably know about here, is with hail pad. So a hail pad consists of a square of styrofoam covered in aluminum foil. And so when the hailstones hit it, they leave a dent. The styrofoam is fairly low density, so they can actually impact. And so this is large hail. And so that's one method. And in a number of countries, there are whole hail pad networks. And hail kinetic energy. Okay, so this is a device to measure hail kinetic energy. And it's automatic and continuously hail recording in real time. So basically, it hits a piezoelectric device, and that sends a signal to a recording device, and that signal is proportional to the kinetic energy. So, and momentum. And a more recent version is the insurance industry, the Institute for Business and Home Safety has another piezoelectric device, and this has been used quite extensively over the last 5 years. And COCORAS, the Community Collaborative Rain, Hail, and Snow Network, has a multitude of hail pads in many locations throughout the United States. And observers often report these, so there are observers who volunteer. And so this just shows the sizes of hail. And what we see here is this is diameter. This is basically a frequency diagram. And so you see in the warm area of Arizona, where it's quite warm at the surface, even if there's hail aloft, a lot of it melts before reaching the surface. Kind of as my guess is in areas at sea level, you need something larger than about a centimeter to make it to the ground as hail. So the really giant hailstones don't melt much, whereas the smaller ones melt completely. And so now let's go to Illinois, where it's not nearly as warm near the surface. Here you see it broader. Alberta, Canada, which is at 1.7 or 8 kilometers above sea level, you see the PDF is much broader. There's not as much melting. And Colorado, again, really hot spot. And New England has some large hail, but because it tends to be warmer and surface generally near sea level, there's a lot more melting. So that just shows kind of a pictogram of how things work. And then radar detection of hail. So we can have radar with dual polarization. So the waves look something like this at the horizontal and something like this in the vertical. And because the hailstones are not perfect spheres, you can get different polarizations. So particles have different shapes and orientations, and horizontally and vertical polarized signals encounter different amounts of water mass and return different signals. And from these differences, you can infer some properties of the hydrometeors. And then differential reflectivity, so ratio of scattered horizontal and vertical power returns, and those are a function of the particle shape and orientation. It's independent of absolute calibration and particle concentration, and it's affected by differential attenuation. But it's a good discriminator between heavy rain and hail. And here are just some of the details. Okay, South Dakota School of Mines and Technology. So when I first started my career at NCAR, I worked a lot with this aircraft and data from it. So there's the aircraft, and this is a hailstorm penetrating aircraft. It has pods underneath to collect information on particle shapes. Here's another one. So a variety of sensors to measure size distributions, shapes, mass, etc. What can I say about this? It was a real workhorse. And this just shows one of the particle probes. So a laser beam shines across, and then a laser beam shines across and is basically measured. The shape of the particles are measured and their size. The skies were not always friendly for this aircraft. Some of the hailstorms it got into were extreme. And this is an example of one of those. You can see it got pretty dinged up. But this is an armor-plated aircraft and just single engine propeller and real workhorse. The T-28 accomplished more than 900 hailstorm penetrations in a series of research projects dating back to 1970. They were in the United States, Colorado, Switzerland, and in most cases, the emphasis was on studies of hail development, for which the T-28, with its ability to penetrate storms containing hail up to more than 5 centimeters in diameter, was uniquely suited. And the T-28 observations of high and updraft structure, high reflectivity regions of thunderstorms have served to characterize the types and concentrations of these particles in these regions and identify the particles that serve as hail embryos. They have revealed that supercooled water is often depleted by ice particle growth in the primary hail growth regions around the edges of the major storm updrafts, as well by incorporating dry air from the outside. Updraft cores may be relatively undiluted, and I'm laughing, I'll tell you why, in large high plains thunderstorms. A study of supercell storm investigated during COPE provides one example of a huge updraft core, 50 meter per second updraft, was relatively free of entrainment effects. So I'll just say one more thing about the aircraft. It was basically retired in 2003. It is retired. And so for about the last 15 years, there's been no way to uniquely get into a hailstorm to make observations. And the problem with that is that trying to evaluate ZDR, differential polarization signatures of hail, are very difficult to come by for that reason. Okay, so basically a little bit about particle size distributions. Some investigators have found that, and I mentioned in my class today, gamma distribution. But so this is a gamma distribution. And if I was to draw a little diagram, but look, this is number concentration, this is diameter. And so a gamma distribution would look something like that. So it's pretty good at getting the tail and the small end. And a few studies have found that they can be described very simply just by a simple equation, but it's not really that simple. So here is, most studies show particle size distributions for Graup and hail are fitted best by an exponential. And that is a gamma without the mu. Mu is the dispersion. And so, this would be better fit by a gamma. An exponential just goes all the way like that. So at a diameter 0, it just hits n naught. So basically, then, there's been really quite a bit of work trying to examine how well exponential fit size distributions, and they're used heavily in models. And Mikhail and I are working on a paper to look at all these different parameterizations and how well they fit observations from the T-28 aircraft. So these are the size distributions averaged during hail encounters per day. And so this shows basically what the form of the size distributions look like. And this is a linear scale. This is a logarithmic scale. So perhaps an exponential looks okay, but you can't really extend it much below there. And these observations are made in cloud, where temperatures are below 0 degrees centigrade. Now what happens in reality is as the particles fall to the surface, these are not going to change much in size. These are going to drop down like that. So gamma would fit observations better at the surface. Okay, so this is another way that hail has been observed. This is Charlie Knight at NCAR, and this is his wife, Nancy Knight, deceased now. And so this is this was at the time the largest hailstone found at the time in 2003. And this was Aurora, Nebraska. And this was actually, I think, Vivian, South Dakota. This is the largest one. I'll give you a little more detail on that in a few minutes. So hailstone shapes vary. They can be conical, as I mentioned, oblate, spheroidal, irregularly shaped, and sometimes with spikes and lobes. Oblate spheroidal is common. So that is, this axis is shorter than that length. Okay, and many have axis ratios of 0.8. And here you see what I talked about, the tree rings. And that represents different growth regimes. Hailstone shapes are less spherical or more oblate with increasing size. So here's an example. Tendency for axis ratios to drop off. And the embryo type, that is what's at the core. So the embryo type, here, this does not look like spherical. So that embryo is somewhat conical. And that is a conical graupel. And typically in Colorado, which has a relatively high altitude and it has a relatively cold cloud base, those embryos are typically conical. And the reason why they're conical is because you don't get a lot of large drops produced in clouds with relatively low cloud bases. Whereas in Oklahoma, which is near sea level, they're often frozen drops like this. So basically then, a drop is lofted to sub-freezing temperatures, and that forms as the embryo. Lobe structures can be found in hailstones, altering their shape either subtly or drastically, and it can make modeling of the shape in models, whether in cloud models, weather research, forecast models, difficult uncertainty. So two kinds of lobe structures on hailstones, and I'll show you some examples. Cusp lobes form in dry growth. That is, those are lobes that have lots of little perturbations. And they form in dry growth, result from a collection efficiency effect where lobes grow faster than their surrounding areas. And mostly when hailstones are tumbling, and I'll show you examples. Icicle lobes look like icicles or melted ice, wetter spongy growth, and then just sort of non-spherical. So can tell quite a bit about how they grew from their shape. Okay, let's go. Okay, there we go. So here are hailstone embryos. They have a lot of an impact on the shape. So impact on shape during hail growth. Distinct early growth mode of large hail suggests that embryo formation, the embryo, the little kernel, is followed by hailstone growth. And so this is an example, as I said, of a conical one. These are conical, and these are spherical, frozen drop. And so 3 identifiable types are conical, about 60%, spherical, about 25%, that is from frozen drops, and bubbly. Bubbly means it probably froze over, took a while to freeze. And so, as I said, there are regional differences. In Colorado, frozen drop embryos are only 6 to 27%. Oklahoma near sea level, 70%. Switzerland is relatively low, 2/3. And South Africa, low areas dominated by it, and in the high areas, dominated by conical. Okay. So as I mentioned, graupel is heavily rimed snow, smaller than 5 millimeters. Here are just some examples. And you wouldn't see it here because it all melt before falling to the ground. And so conical graupel and lump graupel are most common. Here are just some examples I collected a long time ago. This was collected with the T28. And these are the actual particles or photographs of them. And just a little bit of detail. Here's the axis ratio of graupel, and here's the diameter in millimeters, 5 millimeters. So you see this general drop-off in the ratio of height to width. And here's the mean diameter and their mass. And the reason I show this is because solid ice spheres would have a mass something like this along here, this dashed line. So at a diameter here, they have a much higher mass than actual actual graupel particles. So these particles grow with a relatively low density, and it's not until they get above graupel sizes that they have a high density, unless they start off from frozen drops. So the Insurance Institute for Business and Home Safety has been doing lots of recent, basically I should mention that from about the mid-1980s to about 2010, there's almost no work on hail in North America. There was some in Europe, and so, but very little, very, very little. And in fact, there weren't many T28 observations after the mid-80s. And so they in this period here, took up, since about 2012, they took up a lot of observations of hail at the ground. And so they measured lots and lots of hailstones, and they actually made 3D scans for many, many particles and continue to do that. And with those scans, you can tell a lot of information about the hailstone shape, etc. And they measure the actual masses of the particles. And this is, I don't know if I can get a video. This is an example of a 3D scanned hailstone. And I just turned it here. There we go. So you see there's quite a bit of detail. And I want to see if I can actually present this. I'm going to end this for a minute. And if I'm lucky, I may not be. Come on. Okay. Okay, so if I'm lucky, I can actually show you some of these. So let me show you. First, I will show you the Coffeyville one. And so this is a 3D scan we did at NCAR of the Coffeyville one. And you see here its shape. I showed this in my class this morning. There it is. That was the biggest one for a long time, recorded. And you see it probably fell like this. And so the bottom melted and the water shed off the sides, whereas in the backside is relatively protected from the warm temperature. And so that is that one. Now aurora, as I said, some of these can be really irregular. So let me show you aurora. Okay, here's aurora. Look at that. That was the largest one in terms of length. Look at that, though. Is that wild? And let me show you the Vivian. Vivian is the all-time biggie, and there it is. I'll show you a little more in a minute. And then this fell this past summer. This was the Colorado record. There it is. You can see how it probably fell. And anyone want to see a printed version of it? There it is. I can pass it around for those who want to see. I decided because it's too heavy to carry not to print it to weight, okay? But we weighed it. And then I have taken a bunch of these to a vertical wind tunnel in Germany, Mainz, and we measured their fall characteristics and their fall attitude. Okay, and now I'll show you again Vivian. Okay, there's Vivian. And the next view graph I will show, hopefully, will show you how big it actually looked. Okay, where are you, PowerPoint? There you are. Okay. There we go. Okay, so this takes just a second. Come on. And so I'll show you how big Vivian is, if this actually loads up. I'm not sure. There we go. Okay, so Vivian. So this is a picture of Olivia, the daughter of a friend of mine. Okay, there's Olivia holding a print I did of the Vivian one. And so look at that. Doesn't that give you a feeling for how big these are? Why you wouldn't want it to go through a car windshield, that's for sure. Okay, so these are some that I took to the Mainz tunnel, and in order to understand their properties, what I did was I had the same stone, but I had them printed at different densities so I could learn something about how they fall as a function of their mass. And because the Mainz chamber has some turbulence in it, I had it printed with hooks. And so we could suspend them because they would hit the walls. And so Basically, these are based on the masses measured by about almost 3,000 hailstones by the IBHS group, and that's my analysis of it. And so this dashed line here shows this is mass, this is maximum dimension. So a solid ice stone or a solid spherical stone would have a mass that falls along there. And if it had a density of 0.1, it would fall along here. And so these are the actual masses, and this line shows the median, a fit to the median. So you see there's quite a bit of variation in their masses. And that is probably a very important factor that needs to be considered in models, because we know that not every particle in a hailstorm will make it into hail, to grow into hail. And it's this differential sorting that change in mass would have an effect on the terminal velocity for the same size particle. And so there's this it's a very stochastic process. Just a few lucky ones make it into the big stones. And this just shows a similar plot, but for Graupel. And again, mass, diameter, and these are a number of different relationships. But the important thing here is this here is a density of 0.1, or a spherical equivalent. And so you see many of these Graupel particles, all these points and circles, etc., have very, very low density. And that's probably important in determining what gets selected to grow into a hailstone. Because if the particle is too heavy, it's not going to get lofted by the updraft. So it's really a stochastic, complicated process. And so just a couple of physics things. So the basic equation for calculating the terminal velocity from the drag coefficient. And so this is basically the equilibrium force. So particle is falling against the air, and its fall velocity is determined by its mass and inversely proportional to its cross-sectional area. So if you have a giant flat particle, then it's going to have a very low fall velocity. And if it has a very small cross-section compared to its mass, it's going to have a high fall velocity. And Reynolds number is proportional to the fall speed and diameter divided by resistance due to the air. And the air density is very important inversely. So you see at low pressures, because of this relationship, at high altitudes, the hailstone will fall very fast. And at low altitudes, relatively slow. And so there have been all sorts of studies looking at the mass, drag coefficients, terminal velocities of hail. I'm not going to go into these in detail, but an important unknown is whether the hailstones tumble during their growth or whether they fall in a preferred orientation. And that'll have a big effect. Think of that aurora stone I showed you, which looked kind of long and flat. Well, if it's tumbling, its fall velocity will be much higher than it was relatively spherical, and that's because the resistance, the cross-sectional area, is not very high, and so it can fall fast. And several studies, the early studies at least, used that Coffeyville, Kansas stone, and Roos-and-Cart, and they used the Coffeyville one, and they dropped it in a mine shaft and measured the fall speed of the synthetic ones. So basically, Charlie Knight at NCAR had a cast made of the hailstone, and then it was dropped in a, it was a casting, a print was made, a cast print, and then dropped in a mine shaft. And also in a stairwell. And another method, this was quite amazing, is that they had a skydiver descend at the same time they dropped the stone out. And so the skydiver measured the fall speed as it was dropping. I'm not going to go into this too detailed. This just shows the terminal velocity versus diameter for graupel and hail. And these are some different parameterizations that people have used over the years. And it can have what parameterization you use can have a dramatic effect on how you model hail. And so, kind of some hail basics. In order to grow hail, you need an embryo, liquid water, cold temperatures, and that's the crucial thing, the time within the updraft. And it's such a stochastic process. You know, just the right stone at the right place or the right graupel particle can make it. It might have just the right terminal velocity, etc. I don't think that's appreciated enough. And in general, you need a supercell. Supercell is a long-lasting, intense thunderstorm. And so the long lifetime allows it plenty of time to grow. And basically, the physics involved in hail growth, without equations, I didn't want to put them in. Okay, so you have an embryo, and then a drop gets accreted. And so by the accretion process, that's 80 calories per gram release going from a drop to a frozen ice particle. So what happens is the surface of the hailstone warms due to that heating. So it's actually warmer than the air by several degrees, often. In fact, as much as 5 degrees or more. And so the surface is actually evaporating at the same time that you're collecting particles. And if the surface temperature of the hail is warm enough, it can actually have liquid water shedding or spongy growth. And this is the conventional model of how a hailstone would grow. So here's what's called the weak ecoregion. Reflectivity is relatively low. And so the basic idea is that along these streamlines, you know, the updraft goes like that, and then the hail can grow in this region here, right at the top of this so-called weak ecoregion, and then maybe along these streamlines, grow along here, and then cross the streamlines, and then fall out. Just another example of, you know, recirculation. The thought is, you know, they go up and down, etc. And years ago, I did not like that idea. And so we have quite a few observations from the T28. And my general thought was, okay, you have a large updraft here, but the particles don't have enough time to go in the updraft completely and then grow large enough to be able to stay in it. And what we found was that off on the side of a supercell, you can have these little feeder cells, little cumulus congestus. And so what happens then is perhaps a graupel particle or drop starts off in this feeder cell, which is upwind. And then the feeder cell gets sheared off because this big updraft does not allow it to grow. And the particles then start are carried along the wind direction, which is around the storm, and then they have enough time to develop and then fall in the updraft region. So that's my basic thought on how it works, and I showed that. So I want to talk just briefly about hail suppression mitigation. So the idea is to add more ice nuclei. That is, the storms are not, with more ice nuclei or more ice crystals, each ice particle will be smaller if you have more of them. And so the idea is to put more ice nuclei in through the use of silver iodide, which is a good ice nucleus, injected into storms with aircraft. And the National Hail Research Experiment conducted from this period and used silver iodide injected into hailstorms produced 2 volumes of books related to this topic. And I was hired to analyze, I joined NCAR in 1975, to analyze a lot of the ENRI data. And offline I can tell you what happened. Many field projects and scientific studies involving hail suppression were conducted in Western Canada during the Alberta Hail Research Project. But because there was really no strong evidence that hail storms were seedable, the Russian ENRI was based on the Russian model, which showed dramatic decreases in hail with seeding. And we did not find it. We simply didn't find it. And we used a randomized experiment, just like they do in human trials of drugs. You know, we seeded some storms and compared them to storms which weren't seeded, and we could not detect any statistically significant evidence of seeding effects. And that was from the mid-1970s. So that's why hail research languished from the 1980s to about 2010, because seeding did not seem effective. However, seeding operations have gone on in several other locations. And this is amazing that hail cannons are still used. A hail cannon is a shockwave generator claimed to disrupt the formation of hailstorms. And they are in common usage in Europe and Australia. And the idea is that you shoot up something very noisy, loud, that would blow up inside of a storm, and it shatters the hailstones. There's no scientific evidence for their effectiveness. And so here are just some examples. And so you see some of the cannons. Look at them. 1901, 2007, they're more sophisticated. Still don't work. Okay. So basically, I wanted to just provide you some information that you can think about and learn something from. And so I want to conclude by saying that what we still need to know, how graupel hail forms in a wide range of thunderstorms. And we still don't know the trajectories. And perhaps chemistry, tracers like deuterium, might give an indication, or water isotopes, of how they grew, the temperatures. And calibrating radars to nowcast hail kinetic energy and potential damage. And we really need a hail-penetrating aircraft to measure hail size distributions and, if possible, their masses. And there was an aircraft at NCAR which was a Navy aircraft. For this purpose, it was an A-10, which was a very, very tough jet aircraft. And the Navy decided after 5 years at NCAR, sitting in a hangar, they would no longer want this aircraft to fly. So we need one. And then finally, how hail melts from the bottom of from the melting layer to the ground is very important, and how it melts is important in determining how large hail will fall to the surface. That's it.
Perguntas?
Questions?
One thing that strikes me sometimes with hail is how far they come down compared to where the cloud is. A few days ago, I had something that I really thought it was impossible, because I was seeing the CB and several kilometers from the CB, perhaps 10 kilometers from the CB, and there I was getting hail, pretty big, with clear skies and sunshine.
Well, it just says something. The updraft was so strong. There was a tremendous amount of divergence.
Yeah.
And so it was carried way out.
But do you have statistics of how far hail has been observed away from the core?
No, typically though, it's not terrible. It's in the downburst, or the downward moving in the downdraft, so in the outflow region. So maybe there was also a lot of horizontal outflow.
Okay, so I saw the figure you showed about hail mass versus diameter.
Yeah.
And small hail, they were close to the 0.9 density, and bigger hail were closer to the lower density.
Yeah.
So it means small hail is more dense?
Well, probably what it means is it's a little more spherical. And so they become more stretched out with size. And so their mass, the density, probably doesn't decrease, but the mass does, because they become more oblate.
Okay. Thanks.
E mais?
With respect to chemistry, anyone has done some chemical analysis of dropper stones?
They have, and back in the 70s and 80s, they tried to look at the deuterium content to try to infer what the trajectories were. And then nothing since about mid-1980s. And I've been trying to get a couple of people interested in looking at the water isotopes, because from water isotopes you can tell something about the temperature at which they grew. And the other thing we've actually, I wish I took a picture of it, we actually instrumented some of our printed stones with accelerometers and GPS. And so what we want to do is take balloons and release them at the base of a hail-producing thunderstorm, and maybe track them as they're going through.
Oh. Like the Twister movie.
Yes.
I think a lot of people here don't know what a spongy hail is. Could you explain?
Spongy hail is, so think of a sponge as being the ice mass, and then filling the sponge with water, and so it's squishy. Squishy.
It's really squishy. You squish it and it bounces it. Yeah. It's kind of rare, right?
Yeah, it's rare.
I saw in Colorado. So. No, not here. Never seen here. Any other questions?
Okay,
Nope.
well, I'm around, so again, thanks for inviting me.
Let's thank our speaker again.
Yeah, feel free to come down and near Mikhail's office.
Nice presentation.
Thanks. Thank you very much.
Actually, I saw one of those cannons in California.
Yeah.
They have, I think it was over California. Yes. It was in a peach orchard.
Yeah, right.
Yeah, they have.
They're trying
they
to
are spending a lot of money on that. I went there like last 2 months ago, and I went to some farms there, and they use it. They are spending a lot of money.
Isn't that just craziest thing?
Yeah. Have you seen it? No. If you look at on the internet, I think you find some.